Hey everyone, let's jump right into something we've literally all experienced. Picture this. You're sitting in a lecture hall. The professor is up there explaining a sorting algorithm, or maybe some complex new API, and it makes complete, total logical sense, right? You're nodding along, taking notes, feeling pretty good about yourself. But then, you step into the lab, you open a blank project in your IDE, stare at that blinking cursor, and suddenly, total paralysis. You just freeze. Why on earth does the code look so brilliantly simple up on a projector, but feel like an absolute alien language when it's time to build it on your own? Well, that gap, the space between understanding a concept and actually executing it, is arguably the biggest hurdle in software engineering.
So let's dive straight into this engineering playbook. We'll be looking at the shift from passive to active engineering, breaking down logic and problem solving, mapping out backends and databases, mastering the art of independent debugging, and finally, building your own debugging encyclopedia.
All right, first up, passive to active engineering. This is all about shifting your mindset from being just a transcriber to actually being a builder.
Look, sitting in class and just copying syntax down, that's not engineering. That's transcription. And transcription is absolutely not going to help you when you're stuck in the lab. Passive listening is what most of us default to, right? Just copying the professor's slides and waiting for them to give us the answers. But active engineering, that requires a totally different, much more intellectual approach. When your professor introduces a loop or a condition, don't just sit there waiting for the syntax. You've got to write pseudocode in your notebook first. You need to mentally trace the state of those variables. Challenge yourself. Ask, okay, what's the base case here, or what's the invariant of this loop? Do this before the solution is ever shown on screen.
Moving on to Section 2. Logic and problem solving. Think of this as your boots-on-the-ground battle plan.
This mindset shift completely changes how we handle lectures versus labs. During a lecture, when a new problem drops, don't look at the solution. Just stop for a second, set a 5-minute timer, and jot down 3 brute force approaches. Seriously, even if they're horribly inefficient, you're engaging your brain. You're strategizing, asking yourself, wait, why did they use a hash map instead of an array here? And then, when you actually get to the lab, it's all about raw, unassisted execution. Check out this rule. No autocomplete for the first 30 minutes. None. 0. You have to force yourself to type out every single bracket and keyword manually. It's tough, but it builds that crucial muscle memory and locks in your syntax retention.
But hold on, before your fingers even touch that keyboard in the lab, you need a strategy. This is where the input-output-edge strategy comes in. You basically have to solve the problem on paper first. Step 1, write out a sample valid input. Step 2, write down the exact expected output. And step 3, this is the fun one, write out the most annoying edge case you can possibly think of. We're talking null values, empty arrays, weird negative numbers. Map out the logic on paper step by step. Because if you skip this and jump straight into your IDE, I guarantee you'll just end up blindly tweaking logic, crossing your fingers, and hoping to magically pass those test cases. Which brings us to a personal favorite and a totally time-tested practice, Rubber Duck Debugging. This is simply the practice of explaining what every single line of your code does, out loud, in plain English, to an inanimate object, like a rubber duck, or maybe to your lab partner, before you ever hit run. I know it sounds kind of silly, but it is incredibly effective. Why? Because honestly, if you can't verbally explain your logic out loud to an empty chair, you just don't understand it yet. It forces you to slow down and really articulate your mental model.
All right, part 3, backends and databases. This is where we start mapping out the flow of data. When you start scaling up to web servers, it's not just about the code anymore, it's about the entire architecture. I highly recommend actually drawing this architectural flow map right in your notes during a lecture. Literally draw the arrows, from the client, over to the router, down to the controller, the service, into the database, and all the way back as a response. For every single new endpoint your professor brings up, annotate this diagram. Note exactly where the business logic lives and exactly where the validation kicks in. Visualizing this flow is basically your master key to understanding back-end development. And notice how this strategy changes when you move from the lecture to the lab. In lecture, you're mostly memorizing join logic and staring at entity relationship diagrams. But don't just stare at them. Actually speak them out loud. Literally say, okay, one user has many orders, to lock in those foreign keys. But in the lab, it's a whole different ballgame. You need to run debug mode line by line. Watch how the framework parses JSON in real time. Log your SQL queries. Compare the query you thought you wrote against what actually hit the database. Active observation like this is hands down the best way to catch massive performance bottlenecks, like that infamous N+1 query problem.
And of course, working with APIs means you really need to understand how they talk. These right here are your core HTTP status codes. You've got 200 and 201 for your success responses, 400 and 404 for those client-side errors, and 500 for when the server just completely fails. But here's the kicker. Before you ever try connecting your API to a database, use instrumenting tools. Get into Postman or Insomnia and test your endpoints with hard-coded JSON tied directly to these status codes.
Next up, Part 4, Master Independent Debugging. Honestly, this is the ultimate boss fight of programming.
This right here is the climax of our playbook. It starts in the lecture, where you have to practice ignoring all that stack trace clutter before the professor even runs their broken demo code. And in the lab, well, 30 is your magic number. You've got to adopt a strict 30-minute no-hands-up policy. When your code inevitably breaks, and trust me, it absolutely will break, you are forbidden from asking a TA or a friend for help for exactly 30 minutes. You have to rely completely on your own wits.
So what exactly are you supposed to do for those 30 minutes? You use your primary weapon, the debugging triad. Step 1, read the exact error. Don't skim it. Copy and paste the trace and highlight the exact line number. Step 2, binary search commenting. Just comment out half your code to isolate the broken function. If the code runs, boom, your bug is in the commented half. And step 3, the println army. Print your variables and their types out right before the line where it crashes. I can't emphasize this enough. Like 90% of bugs are just simple null pointers or incorrect data types. Trust me, this tactical workflow is going to save you hours of aimless frustration.
Now, what if those 30 minutes are up and you're still completely stuck? That's when you initiate the Fresh Eyes protocol. Stand up, step away from your screen, go grab a drink of water, and then come back. Look at the very first line of the error again. It's crazy, but stepping away physically almost always reveals some wildly simple mistake. A tiny typo, using a double equals instead of a triple equals, or maybe a plural table name instead of a singular one. Sometimes your brain just needs a quick reset.
Finally, Part 5, the Debugging Encyclopedia. This is all about building your interview arsenal.
So let's say you did everything right, you're still stuck, and now you're just sitting there waiting for a TA to come help. We'll turn that idle frustration into active interview prep using the split screen strategy. On the left side of your IDE, keep your broken code, but on the right side, open a totally blank notepad. On one half, write what I expect to happen, and on the other, write what actually happens. Visually splitting your screen like this forces you to confront the logical gap in your mental model. It transforms a really frustrating wait time into super productive troubleshooting.
And when you finally crack the bug, you do this. You write a one-line comment directly in your code. Something like, fixed, use deep copy instead of reference copy. By dropping a note like this after every major bug, you are essentially building a highly personalized debugging encyclopedia for your future self. When it's time to prep for technical interviews down the road, you won't be skimming through some generic textbook, you'll be reviewing your very own battle scars.
Which leaves us with one final, absolutely crucial question. Next time you sit down in a classroom or a lab, will you choose to be a passive transcriber or an active engineer? The playbook is right here in front of you. That gap between the lecture and the lab, it is entirely bridgeable, but only if you decide to actually apply these strategies in your very next study session. So, what are you going to build?